Okay, today we're going to learn about how to find improper integrals. Okay, all of the definite integrals we have encountered have had finite intervals of integration. In many applications, however, we will concern with integrals that are unbounded. That's integrals of integration, such as integrals that are these types of integrals are called improper integrals. So example, this is where our upper bound or lower bound is not a constant, but instead negative or positive infinity, as you can see in these three examples of improper integrals. Now, what the cool thing is about improper integrals, we tie integrals and limits together. So we'll rewrite this as the limit as a goes to negative infinity of the integral from a to b of f of x dx. And so now I can evaluate that because I have a and I have a b. I have a upper and lower bound. If the upper bound is the infinity, would say the limit as b goes to infinity of the integral from a to b of f of x dx. If both of them are upper and lower bound, we would first break this up with some constant, any number in between negative infinity and infinity. So I'd rewrite this as the integral from negative infinity to c of f of x plus d of x, plus the integral from c to infinity of f of x plus d of x. And then I just do what I did in the first and second examples. Okay. And then we do our improper integrals. So we have to break it up first. And so when we break this up, this becomes the limit as a goes to negative infinity of the integral from a to x f of x dx, plus the limit as b goes to infinity of the integral of c to b of f of x dx. We're going to learn some new terminology. So the terminology we're going to learn is if a limit exists when we do improper integrals, it is said to be convergent. That means it converges to a value. If the limit does not exist, the improper integral is said to be divergent, meaning it diverges and does not approach a single value. So let's do some practice problems here, and we're going to evaluate these integrals, and then we're going to say if it converges or diverges, and if it converges, what it converges to. So we're going to do the integral. Notice our upper bound is infinity, so we're going to set this up as the limit as b goes to infinity of the integral from 2 to b of 1 over x dx. Now we just do the integral like we do normal, so I'm going to bring down that limit notation. And we start on the inside, so we evaluate this integral. So that integral is going to be the natural log of the absolute value of x. Evaluate it from 2 to b. Okay, so let's evaluate that. So this becomes the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of 2. And then we're going to actually do the limit. So we're going to evaluate this as b goes to infinity. So think about what happens to the limit as the limit of the absolute value of b when b is infinity. Well, that goes to infinity. So we have infinity minus the natural log of 2, which is just infinity. So this is a divergent integral because it goes to infinity. Okay, next example knows our upper bound is also infinity. So we're going to go limit as b goes to infinity and replace that infinity with a b. And then we're going to integrate this. Well, the integral of this is the arctangent or the inverse tangent of x, evaluated from 0 to b. Evaluating that integral gives us the arctangent of b minus the arctangent of 0. And now we know the angle whose tangent is 0 is 0. So I can just rewrite this as the limit as b goes to infinity of the arctangent of b. And then I ask myself, okay, since the arctangent of b goes to pi over 2 as b goes to infinity, I would say this integral approaches pi over 2. It converges to pi over 2. Okay, in example 3, our lower bound is the infinity. So I'm going to rewrite this as the limit as a goes to negative infinity of the integral from a to 0 of e to the x dx. So inside out, so we're going to first evaluate the integral. And the integral of e to the x is e to the x, evaluated from a to 0. And then that'll be the same as e to the 0 minus e to the a. We know e to the 0 is 1. So basically we have 1 minus the limit as a goes to negative infinity of e to the a power. Well, think about the graph of e to negative e to x as x goes to negative infinity. We know that approaches the horizontal asymptote of 0. So we know e to the a goes to 0. And so our answer is 1 minus 0, which is 1. So this integral converges to 1. Okay, for b, we have a double improper integral. So we got to break this up first, choosing any value between negative infinity and infinity. I'm going to choose 0. So 0 is usually a good one. 1's also one that works pretty easily. So I'm going to break this up as the integral from negative infinity to 0 of e to the x over 1 plus e to 2x dx plus the integral from 0 to infinity of e to the x over 1 plus e to the 2x dx. For the first integral, I'm going to set it up as the limit as a goes to negative infinity of the integral from a to 0 of e to the x over 1 plus e to the x squared, or e to the 2x dx. And then here, this one's going to be the limit as b goes to infinity of the integral from 0 to b of e to the x divided by 1 plus e to the 2x dx. Okay, so let's look at that denominator, 1 plus e to the 2x. Now I can rewrite that as 1 plus e to the x quantity squared. So I have an a squared over an x squared term. So this is our inverse tangent function, where our u is e to the x. So this is the inverse tangent of e to the x when I integrate it. So I have the limit as a goes to negative infinity of the inverse tangent of e to the x evaluated from 0 to evaluate from a to 0. So we have the inverse tangent, the arctangent of e to the x evaluated from a to 0, plus, and I got the same integral on the side, the limit as b goes to infinity of the inverse tangent of e to the x evaluated from 0 to b. All right, so that gives us the arctangent of 0, which is the angle whose tangent, e to the 0, which is 1, minus the arctangent of e to the a, the limit as b goes to infinity, of the angle whose tangent is e to the b, minus the arctangent of e to the 1, which is e to the 0, which is 1. So evaluating that, I get pi over 4 minus the limit as a goes to negative infinity of the inverse tangent of e to the a plus the limit as b goes to infinity of the inverse tangent of e to the b minus pi over 4. So the pi over 4's cancel out. Now let's see what happens to our arctangent as e goes to infinity. So as e goes to infinity, e goes to negative infinity, that's going to give us 0. And as e goes to infinity, that's going to give us pi over 2. So 0 plus pi over 2 is pi over 2. So this one converges to pi over 2. Okay, now we're going to look at improper integrals with infinite discontinuities. Now, this can occur, so the second type of improper integrals that happen is not as obvious as the first, and this is where you have infinite discontinuity at or between your limits of integration. So it's not going to be set up with, you're not going to see a limit to the integral to infinity or negative infinity. So you're going to have to figure this one out. And basically this happens when we have asymptotes. So if I have the integral from a to b of f of x dx, and it has an infinite discontinuity at the endpoint b, I would rewrite this as a limit as c goes to b to, from the left of the integral from a to c of f of x dx. So notice here, if the discontinuity, the asymptote occurs at our upper bound b, so notice our integral does not reach b, then our upper bound will replace with our letter c, and we'll use the limit. Our second situation is if the undefined, the infinite discontinuity occurs at our left integral, at a. So then we'd set this up as a limit as c goes to a to the right hand side of the integral from c to b of f of x dx. So notice here the left-hand integral is what we cannot reach. And so we replace that with c, the lower bound with c, and evaluate it. Okay, a last situation occurs if our asymptote or our infinite discontinuity occurs inside our interval. And so when we have like this, it exists at A and B are endpoints, but it doesn't exist somewhere inside the interval. We need to split this up at that point of discontinuity. As the integral from A to C of f of x dx plus the integral from C to B of f of x dx, where C is the point of discontinuity, or the x value of our discontinuity. Okay, so let's look at this one. We have the integral from 0 to 1 of 1 over the cube root of x. Now remember, can't divide by 0, so x cannot equal 0. So we have discontinuity at x equals 0. Or infinite discontinuity at x equals 0. And so I need to rewrite this integral as, okay, so we're going to rewrite this integral as the limit as b goes to 0 from the positive side of the integral from b to 1 dx divided by the cube root of x. So first we're going to find the limit, the integral. And so I'm going to rewrite this as x to the negative 1/3 power. And then the integral of x to the 1/3 power is 3/2 x to the 2/3 power, evaluate it from b to 1. Okay, then we're going to evaluate that integral. Now we're plugging in 1, we just get 3 over 2, and then we have the limit as b goes to 0 from the positive side of 3/2 b to the 2/3 power. Now since b to the 2/3 power approaches 0 as b goes to 0, we would say that this is 3/2 plus 0, or 3/2. So this integral converges to 3/2. All right, so here we know we cannot divide by 0, so x cubed cannot equal 0, or x cannot equal 0. And 0 is in our interval of integration here, so we have infinite discontinuity at 0. So we need to split up this integral from negative 1 to 0 of our 1 over x cubed dx plus the integral from 0 to 2 of 1 over x cubed dx. So we split up that point of discontinuity of 0. Then we do our upper bound infinite discontinuity for the first integral. And we're going to rewrite this as a limit as a goes to 0 from the left-hand side of the integral from negative 1 to a of 1 over x cubed dx. So if I go ahead and evaluate that, that's going to be negative 1 over 2x squared, evaluate from negative 1 to a. And then our second one, we're going to set that up as the limit as b goes to 0 from the right-hand side of negative 1 over 2x squared from evaluate it from b to 2. So since negative 1 over 2x squared approaches negative infinity as x goes to negative 1, this diverges. I don't have to do any more. As long as in one term, if we're adding or subtracting, it diverges to another diverges, it totally diverges. Okay, here's an example of a double improper integral. Okay, we have the infinity as our upper bound, so that's improper, but we also cannot we cannot equal 0, or we cannot equal negative 1. And so 0 is the only one in that interval we have to worry about. So our upper and lower bounds are improper. So they also go to infinite discontinuity. So we would set this up as 0 to some value. Pick whatever number you want. I'll pick 1 of our function plus the integral from 1, that random number I chose, to infinity of our function. And so 0 from the right-hand side. And let's figure out what our integral of this would be. Let's do u is equal to our x to the 1/2. And so the derivative of that would be 1/2 x to the 1/2 power to the negative 1/2 power, which is 2 the square root of x over dx. So that could be rewritten and then we can factor out our constant 2. And so we have 2 times the integral of 1 over u squared plus 1. Oh, that looks familiar. That's our inverse tangent or arctangent function integral. So that'd be 2 times the arctangent of our u. Our u is the square root of x. So that's our indefinite integral. So let's plug that back into our limit notation here. So this is going to be the limit as b goes to 0 from the right-hand side of our integral from b to 1. And then we evaluated that. So I figured out that improper integral. So I'm just going to write 2 arctangent of the square root of x, evaluate it from b to 1, plus the limit as a goes to infinity of 2 times the arctangent of the square root of x, evaluate it from 1 to a. All right, so we get 2 times pi over 4 minus 0 plus 2 times pi over 2 minus 2 times pi over 4. All right, so the 2 times pi over 4s cancel out, and that leaves us with pi. So this integral converges to pi.